Mathematically, we can represent a Gaussian distribution with a Gaussian function, which is why it's known as a Gaussian distribution. So we can write this as y equals 1 over sigma times the square root of 2 pi times e to the minus x minus mu, or x bar if we don't have infinite data, squared divided by 2 sigma squared. So this is the mathematical description. We won't use this equation very much, but just to know that this is where this comes from. One thing to know is that if we take the area under the curve of our distribution for a given part of the plot, it will tell us the probability of getting a value, of measuring a value within a particular range. So what we're going to do is look at a plot. This is what's called a living graph that comes with the textbook. And so this is a Gaussian distribution, and this has some text here, but what we're going to look down here is at the bottom. So this is a generic Gaussian distribution, and we can see what happens as we change. Look here. So what we're doing right now is integrating this area out. From here we can adjust this, and this is where our standard deviation is equal to 1, and our mean is equal to 0. We can change this. Really, all it will do is just change the numbers at the bottom here. Say we have a standard deviation of 2.5. So now, our x-axis is changing, but the overall shape of this is not changing because this is still just a Gaussian distribution. So because the x-axis scale is changing, it's kind of hard to see any meaningful change here. We'll keep the deviation at 1 just to make this a little bit easier and put this back to 0. But what we're looking at here is the area under the curve here. So if I drag this the other way and I make it a little bit more clear. So if I say go between, here and here, the area under here is 0.1359, or there's a 13.6% chance that we measure a value within this range. That's at between -1 and 2 standard deviations away from the mean. So let's look at what's the area inside of something that's, say, plus or minus 1 standard deviation from the mean. Okay, so if we're considering all the values that are within 1 standard deviation, that represents about 68% of the possible values we can have. So about 68% of our measurements will lie within 1 standard deviation of the mean if we have actual random Gaussian data. As we increase this, we'll cover a larger percentage of the data. So at 2 standard deviations, plus or minus 2 standard deviations, we're at 95% of the values will lie within there. And often what's considered sort of the standard that we use in analytical chemistry, at least, is plus or minus 3 standard deviations, because that will contain almost all the possible values that we could have. And that's 99.7. I think it's actually 99.5. Oh, it is 99.7. I had my values wrong. 99.7% of the possible values. So if we measure a value, we would really expect it to fall within this plus or minus 3 sigma range. We can, of course, look at this the other way around, that if we take a measurement and we have a good idea of what the standard deviation is and the mean, we can also say that something would lie outside only about 0.3% of the time.